Welcome back to the classroom. My name is Mr. Wong, and today we're going to be looking at solving an exam problem using projectile motion as the topic. This is the 2015 paper, question 21, and as you can see, we are launching a projectile horizontally off a platform. The projection will look something like that, and it will land at the designated spot on my question. Okay. So from here, we get a set of data that says the measurements of the distance traveled by the projectile based on its initial velocity. Now, in this question here where it says initial velocity of the projectile, do take note that because this has been launched horizontally, there is no vertical motion or no vertical initial velocity, so to speak. So the initial vertical is actually 0 for each scenario that we have. And on this chart that we have here, or this table here, these are all the initial horizontal velocities, and this is the range of the horizontal displacement that has formed. Now, let's have a look at what the question wants us to do. Okay. So first part of the question, it says to graph the data on the grid provided and draw a line of best fit. So let's try and draw out this chart here. The first data point, if you want to try and reference back to this point here, 1.4, I'm going to try and show the 2 pages. So you'll see me graphing it as the data is shown to you. Okay, so there's my data there, and there is my chart there. So we start off with an initial velocity of 1.4. We can see that each box goes up by 0.1, so 1.4 is here. And we have a range of about 1 meter. So the first point is roughly around here. Now some of the points I might draw here might be a little bit out of position, just because obviously I'm trying to do this on the screen. If you're doing this on paper, it's probably a little bit easier. 2.3, and it goes to 1.7, so roughly around here. We have 3.1, it goes to 2.2, so we have this spot here. We have 3.9, which is roughly 2.3, so 2.3 is roughly this position here, I believe. Yep, looks like it. And then we have 4.2, and it is at the mark of number 3. Okay, so that's what we have here. It says the graph, draw a line of best fit. So for most part, if I follow this, it looks like a straight line of best fit. So obviously in a context like this, you use a ruler and you try and draw a straight line. Okay. What you can also see here is this data point here doesn't quite match up with the trend that's been drawn here. So what we could probably say is this is our outlier in our calculation. So I'm going to draw the line of best fit the best I can freehand. I'm going to use a nice little colored pen. So your line of best fit should always start just a bit before your very first point, and it should end a little bit after your very last point. It should go through your data points. It shouldn't be touching, so it shouldn't be connecting dots, but rather just going through them as an average if you can. So that's what I've drawn here. Okay. Now, obviously, we do have an outlier here, so we do need to factor that in, or at least indicate to the marker that we see that as an outlier. So I'm just going to circle this, and I'm going to say that this is my outlier of my graph. Okay, just so the examiner knows that I didn't consider that as my final answer. Okay, so that's relatively straightforward to do. Our second part is to calculate the height of the platform. So the height of the platform, we're trying to calculate SY. Okay, so we know that SY equals to UT plus half AYT squared. Okay, so that's relatively easy to do. We know we're trying to find SY here, so that's what we're trying to find. Let's just write out everything we need. UY is 0, so this equation will just transform itself to half AYT squared. AY is the acceleration due to gravity. Okay. And time is going to be the question mark we want to look at here. Now this is where the graph here comes into play. Now remember the equation for horizontal displacement. Horizontal displacement is equal to ux multiplied by time. Okay. Now let's have a look at what this is. Distance traveled from the base of the platform, so that is our Sx. Initial velocity ux, that's what we have. So maybe we have to do something with the area, or maybe we need to use the gradient value to help us find the overall time. There might be some information here. The best way to work it out is let's try and match this equation that I've drawn here with the graph that I've created here. So on the top is Sx, so Sx over initial horizontal velocity, and we have time. So in this context here, my time will actually be my line of best fit value. So let's use a couple of points and try and find the value for t. So we've got this point here, and I've got this point here. So my value, so t is actually just my gradient line here. That's the overall time taken. And using that, we should be able to find the average time required to go from the top here to the bottom. Because as we know, it's the height of the platform that dictates the overall time it takes to drop to the bottom. So if the height has not changed, then the time it takes to drop should also be the same. So that's the assumption we can make here. So let's have a look at what these points are. So the first point we have here, 1, 2, 3, that's 1.3. And on my y-axis, that is 9, 8, 7. So 0.7. And on this point here, we have 4. And at this point here, that looks like a 3.9. Is that? Oh no, 2.9, sorry. 2.9. So t is equal to, if you remember the gradient formula, so the gradient is y2, y1, x2, x1. So our y2 is 29, subtracted by 0.7. 4 subtracted by 1.3. So what is that? Let's use the calculator to work it out and see what we can get. Now, one of the big skills that you need to use in HSC Physics is the way of interpreting data on charts. So 1.8148. We'll just use these numbers for now. Okay. As you can see, the numbers that we have are to 2 significant figures or to 1 decimal place. So you can try and do 2 significant figures or 1 decimal place as you see fit. So that's the time it takes for it to drop from the top here down to the bottom. Okay, so let's put this into my chart here. That t squared is 0.8148 squared, and so approximately speaking, let's see what we get. So obviously this is how much we've fallen by. So we've fallen about -3.3 meters if we're doing it in 2 significant figures or 1 decimal place. So therefore, the height of platform is about 3.3 meters. And so that's how you solve this problem here. Okay, so the key point is, there's a couple of points, I guess, to acknowledge that originally, because we fired this horizontally, the initial velocity is just ux. When you graph this out, you need to try and compare to any relevant kinematics formula and see what the gradient value, or maybe the area, tells you. And we worked out that's time, and therefore using our other equations we can work out the height platform. If you've enjoyed how we've broken down this question, going through projectile motion questions, and you feel like this has really helped you improve your understanding of how to interpret diagrams and charts, hit the like button and subscribe. I'll see you next time.